think we're all on the same page now, thankfully. Okay. So, go back a couple of pages. Let's do titration. Those of you that were in lab this morning are experts on this now, right? Generally, we use titration to determine an unknown concentration. We do it by reacting one solution with another and stopping when the reaction has just finished, okay? When we've added just enough of one reactant to completely react with the other stuff that we're adding it to, okay? So, for instance, if we're reacting an acid and a base, HCl and sodium hydroxide, the net ionic equation, if each of these got broken up into their ions, right, we would have, here, that one would get broken up too. We'd have sodium and chloride be spectator ions. The net ionic equation is just H plus and OH making water. We actually showed that reaction last time. If we have just those substances in that net ionic equation and we show a titration happening with those things, it makes it a little easier to understand. So say we have a burette. There's our burette. That's the tube that contains the thing that we're adding, and the burettes has markings on it so you can measure the exact volume that you've added. In lab, we actually use a pipette in order to do a microscale titration, but it works exactly the same way. Okay? We've got hydroxide up here. We've got H+, so here's our acid. Right? That's from HCl. But the H+ ions are the ones that actually are reacting in this. You see from the reaction here, H+ and OH can combine together to make water. So with every OH that we add down in here, it neutralizes one of those H+'s and makes water. Okay? We continue adding it. It continues reacting with these H+ ions down in there until we get to the end point, or the equivalence point. Let's write end point there, because sometimes it's called that, where we've added just enough. Right here we're adding this, where we've added just enough from the burette to completely neutralize the reactant that was there in the beginning. Okay? That's the equivalence point, or the end point, when the reaction is complete, or when equal moles of both reactants completely react with each other. Okay? Say, for example, if we had, 2 moles of H+ down in there, it would take 2 moles of OH minus added in order for this to be totally neutralized. Uh-oh, is it doing it again? We had a good amount of time where that never happened. Okay. So, if we started with 2 moles in here, it would take 2 moles from there to completely neutralize it. So, typically, we use an acid-base indicator to change color in order to signal the endpoint. For instance, phenolphthalein turns pink when the solution has excess hydroxide. So when the solution is basic overall, we get a pink color. As you'll see doing this in lab, what you're aiming for is a very light, faint pink color, because what you're actually detecting is excess hydroxide. You want to get it so that you're just barely seeing some excess hydroxide. Okay? If it's bright pink, that means you've got a ton of excess hydroxide in there. You've actually gone way past the end point. Okay? So by necessity, you have to go past it just a little bit in order to see any color, but you want to minimize that for that to be as accurate as possible. Okay? So here's an example of a problem that we can do with titration. It's nothing special. It's really just a solution stoichiometry problem, okay, along with calculating a molarity at the end. So let's say that we have 25 milliliters of HCl of unknown concentration, and what's helpful sometimes is draw a little picture to help visualize this. So I'm going to draw a flask here. Here's our HCl. There we've got 25 milliliters, unknown molarity. Okay, unknown concentration. That was titrated with, so that means in the burette, a little stopper there. Okay, in the burette we've got sodium hydroxide. That's what's getting added to the HCl. We had to use 12.45 milliliters of 0.100 molar. Okay? You have to know the concentration of one of these solutions, okay, in order to figure out the concentration of the other. In lab, what we actually do, the first step is figuring out what the concentration of that sodium hydroxide is. So titrating that sodium hydroxide with a certain amount of a solid acid down below. Okay? That's a standard way of starting it. But then once you know the concentration of that sodium hydroxide, you can titrate your unknown acid in order to get it to work. So first step that tends to be helpful is having your two reactants here, drawing reactants. Okay. Drawing the two products that are formed. What are the two products here? NaCl, AQ, H2O. What phase label do we give H2O? Okay. That's important because this mole ratio is 1:1. Okay. That's going to be important. Okay. So let's start with the solution that we added. Okay. We had 12.45 milliliters of 0.100 molar sodium hydroxide. And remember this molarity, what does that capital M stand for? Moles per liter. Okay. So if we start a conversion problem here with that 12.45 milliliters of sodium hydroxide, let's be specific here. And I have this conversion factor right here. What should I probably convert those milliliters into first? Let's convert those milliliters into liters. Okay. That looks good. And then, since I know the molarity of that sodium hydroxide, I'm going to say 0.100 moles per what? 1 liter of solution. Okay. That would allow us to calculate moles of sodium hydroxide that were added. Okay. And in fact, you could probably do this one in your head, because I divide by 1,000 and then multiply by 0.1. So I'm going to be taking that down by 3 powers of 10, or by 4 powers of 10. 1, 2, 3, 4. So 1.245 10 to the minus 3 moles sodium hydroxide were added. Okay. Pretty much when you're given a volume and a concentration, you can use them, you can cancel their units to figure out how many moles of sodium hydroxide were added. Okay. But this was a titration. Okay. We didn't just add some random amount of liquid from that burette. We stopped when the reaction was finished. So what does that mean about those 1.245 times 10 to the minus 3 moles of sodium hydroxide? What does that also mean? Yeah, that's the equivalence point. So what do we also know about that 1.245 times 10 to the minus 3? That, yep, okay. That equals moles of HCl originally. Okay, and that's because that's the equivalence point. Okay. If it's a 1-to-1 mole ratio, you can just say that's equal. Okay? If it happens to not be a 1-to-1 mole ratio, you could have said, you could have done something like that. Right? You could have set up a mole ratio. Okay? I'm just going to say that, something like that. Okay? You could have definitely added that to the end using their coefficients. But if it's a 1-to-1 mole ratio, okay, they're just equivalent to each other. So the moles of sodium hydroxide we've added are equal to the number of moles of HCl that were originally within that solution there. Okay? The question asks, what is the molarity of HCl? How do we calculate molarity? Molarity equals what divided by what? Okay, so the molarity of that HCl solution is going to be moles of HCl divided by liters of that original solution. Okay, we're thinking back here. Okay, we calculated how many moles must have been dissolved in there. Okay. But we divide that over how many liters the solution has to calculate its concentration. Okay? So 1.245, 10 to the minus 3 moles divided by what? Yep, 25.0 converted into liters, right? 25.0 0250 okay. Anybody get an answer for that? See if you got the same thing that I did. Yeah, go ahead and punch that in if you haven't yet. 0.0, yep, that's what I got. 0.0498. What unit? Yeah, molarity or molar. HCl. Okay. So, pretty much any titration problem will take some sort of path like this, okay, where we figure out moles of one thing, we set that equal to moles of the other thing because that's what happens at the equivalence point, and then we divide by how much volume those moles were dissolved in to figure out that concentration. Okay? So that's the general method for that. You're going to do some extra calculations beyond this in lab, or you did them this morning. You can calculate a mass percent, and if you know grams of the original solution, and you can calculate grams of one of those components. Okay? Yeah, go ahead. Definitely. Yep, absolutely. That's a second semester calculation, but pretty much a whole month will be spent on acid-base equilibrium, pH, stuff like that, in second semester Gen Chem. So yeah, absolutely. You could calculate the initial concentration. You could calculate the pH at any point during this titration. Okay? You can actually make a graph that goes volume added versus pH, and it'll start out very acidic, like that. As you're adding sodium hydroxide, it neutralizes some of that, but then as you approach the equivalence point, it shoots up, and now we've got excess base that's happening in there. So, all right. So you'll have a chance to practice titration problems, not only in lab, but in the mastering chemistry that you'll be doing for Sunday night. Okay? It's really just an application of the stoichiometry, the solution stoichiometry problems that we've been doing so far. Okay? The only new piece of information is knowing that at the equivalence point, it's pretty much you have added directly the ratio that's required for those two to react perfectly with each other. Okay? That's the idea. So if it's a 1-to-1 mole ratio, you can set the moles of this one equal to the moles of that one. That works pretty well. Okay?